Okay, Bismillahirrahmanirrahim. So let's start this lecture. This lecture is about the design of welded joints. And as we have discussed in the class, we have two cases of the welded joints. One in which the welding is actually is in the beams, and second in the plates. But there could be a possibility that the geometry of the weld is such that both type of cases are applicable on the same problem. So, before going into the this complex case, first let's start with the basic concept of the weld joints. So, this is the problem from exercise example 2. So, let's start with this problem. So, as you can see in this problem, you have a weld which is actually a circular weld here. It's a circular weld, and if you look at the cross section of this weld, looks like this. It's a circular weld here. And what we need to find is design a circular fillet weld joint. So whenever in a problem it comes that design a circular weld or fillet weld joint or a weld joint, you have to find S. S is basically the size of the leg of the weld. This is the requirement in the problem. The problem says draw a free body diagram and the yield stress of the weld material which we're using as a welding material is 600 megapascal and the factor of safety is 1.5. So let's start with the problem. So generally we have to perform two kind of analysis. One is generally called as qualitative analysis, and second is called quantitative analysis. What the difference between these two? First, the qualitative analysis, we want to find what type of stresses are there in this joint because of this load. So we have two loads here. One is here, one is here. The first concept that we're trying to understand, or first analysis we are going to apply, is perform a qualitative analysis, which is what are the nature of stresses that exist or that exerted on this circular weld. And after then, when we evaluated the total stresses in the weld, now we have to actually uh, find out the values of it. So, what are the quantification, what are the quantity of these stresses? And at the end, we have to just use it to find the size of the weld. So, let's start with this problem. So, let's say we have two loads. So, we call this as P1. This is your P1, this is your P2. So your P1 is actually 2000 Newton and your P2 is actually 2500 Newton. So we have two, so we have two loads. One is P1, second is P2. P1 is P2 is 2500. Now let's say if we consider the P1 only, let's say there is no P2 here. For time being, we consider that there is no P2. So what happens is if I directly transfer this circular well as a centroid, and because the circular well it's symmetric at both planes, it's symmetric in the vertical plane, it is also symmetric in the horizontal plane. So in both these planes, it's a symmetric weld. That's why its geometry lies exactly or centroid lies exactly at the center. So if I translate this load directly at this point at the center, which if I again draw a free body diagram, this is your free body diagram, let's say. So one if I apply directly translate a load at this point, which is P1, so what happens is due to this P1, we have a direct shear, and the direct shear has the magnitude of, we call it tau D1. Tau is the used for shear stress, and D is the for the direct shear and one is due to P1. Now the direction of the direct shear is same as that of the direction of the load. If this load is downward, your direction is also acting downward. If the load is upward, your direction will also be on the upward direction. The second kind of if let's say if I translate a load at this point, let's say this point now load is at this point, I can translate this load along the line of action. So along this line, if I translate a load at this point, so what happens is, so we have now another stress which is the bending stress, and bending stress requires the moment and the section modulus of the weld. So because of this application of the load at this point, which is this, it tends to bend the beam in the anti-clockwise, in the clockwise direction. This P1 at point B try to rotate this beam in the clockwise direction or try to bend the beam in the clockwise direction. And because the beam in the clockwise direction, the bending stress is also downward. So we call it sigma B1. Clear? So here we can also write, because sigma tau D1 and tau sigma V1 in the same direction. So we can now write another stress. I use a different color for it. So this is sigma B1. Clear? So due to this load, because I can translate this load along these lines, I'm translating this load at first of all at the point which is centroid at this point. Then I have translated load at point B, where the prominent stress is the bending stress. Why? Because we have P and E, the distance from centroid to the where the load is applied. And because if the load exists at point C, we have additional stress which is called torsional shear stress. So what happens is, because of this arm, because of this arm, this stress, this actually load creates a torsional shear stress. Why? Because it tends to rotate. So see, this is the your arm, this is your load, this is your arm, this is torque. The torque tends to rotate this lead in the clockwise direction. So then we have the additional shear stress, that is the torsional shear stress. The problem with the torsional shear stress is that in case of symmetric geometries, like in case of circular weld, the direction of the torsional shear is tangential to the weld. So, for example, let's say at any point along this, because is actually tends to rotate the weld. So, at any point, its direction is tangential. Clear? Like this. These are the directions for torsional shear, and we call it one because due to load one. Now, for the sake of the you can say design, we consider the direction of because torsion shear stress is an infinite direction. It actually exists along the tangent on the circular weld in at every point. So we take the direction of the weld which is along the other stresses. So we call it as tau T1. I'm again repeating taking the direction of, because tau T1 is a circular weld, and circular weld is symmetric and both planes vertical and horizontal. So the direction of torsion shear will always be tangential to the point. So because a circle has an infinite point, so it has an infinite direction. So the maximum sum is produced when the torsional shear is exactly along the direction of other stresses. So I only take the downward direction of torsion shear in order to get the maximum sum of the stress. Now, if we look at the load P2, so this is due to P1. Now look at for P2. So because also P2 is in the downward direction with the 2500 Newton. If I translate this P2 again at the point where this centroid, so we have a direct shear due to this load 2 which is called as tau D2. So I just draw free body diagram just in case that there is no mix up, but in the problem in the exam you have to write on the same diagram. So this is tau D2, and this tau D2 is due to load P2, which is 2500. And if I translate the load directly here along this line, so we have an additional bending stress, which is, or you can say, if I move the arm, this physical arm at this point, so this has a bending stress again because downward, it tends to rotate this beam downward. So we have another stress, which is, we call it as sigma B, which is the bending stress, and that is sigma B2. And because of this, we have a torsional shear stress because this tends to rotate the, this is the load, this is the moment arm. Clear? So we have additional stress again because this torsional shear again tends to rotate in the clockwise direction, and we have infinite directions. We will take the direction which is more suitable, and that is the tau T2. Clear? So we have in a circular weld six kind of stresses. For one load, we have three stresses: direct shear, bending stress, and the torsional shear stress. For the second case, we all have same kind of stresses. Both loads are there. Now, the important thing here is try to understand the how they will be added together. So sigma B1 and sigma B2 are considered as normal stresses, whereas tau D1, tau T1, tau D2, tau T2 are considered as the shear stresses. So whenever analyzing the weld joints, we have to first combine the similar kinds of stresses, which means we have to sum up the all the bending stresses and we have to sum up all the shear stresses. Before summing up these, we have to first find the magnitude of this. Clear? So for the magnitude, we just now we have performed the qualitative analysis. Now sorry, I'm again translating the problem here so that we can actually analyze this. Okay. Now, if you look at the problem again, now we have six kinds of stresses. Now, first final stresses due to P1 equals to 2000 Newton. So let's say first find tau D1. Now tau D1 is basically the direct shear, which is nothing but P over A. The simplest formula of tau D is P over A. Now P is equal to know is 2000, and the area is the area of the fillet circular weld, and we have to take the base area. So the area of the weld is the outer surface area of the rod or the beam. So which is surface area is pi d, which is circumference into the throat of the weld. Clear? So we have the this beam and your weld. So this time pi d, which is circumference of the weld into the throat of the weld, so which is pi d times t. Clear? Which is the throat of the weld. Now we know that throat of the weld from our class understanding is 0.707 s. So that is equals to 2000 divided by pi. D is the diameter of the rod, which in this case is 3 centimeter. Is yes, 3 centimeter. So just convert into millimeters. So this is 30 millimeter, and throat is 0.707 s. Just calculate here 2000 divided by pi into 30 into 0.707. So what you get is 30 divided by s Newton per millimeter square. Because we've taken 13 millimeters and also in millimeter, so the unit of the stress is Newton per millimeter square. Clear? Okay. Now we have to find the tau T1. For tau T1, we know its relation is TR over J. Clear? Now T is the torque, which is actually equals to the this load P into this distance from this point to the center of the rod. This is your E. Clear? P into E, and what is R as the distance from centroid to the root of the weld, which is nothing but the sorry, which is nothing but the diameter of the rod. So R is equals to D by 2. So that is D by 2, and J is taken from the table. So when you look at the table, these tables are given in exams. So if you look at the table, in this table it's not given. We have to solve the second portion of the table. So see in this table, the this is given. The circular weld geometry is given, and its values of the polar moment of inertia and shear modulus also given. So we just write here J is equals to pi t d cube by 4, and Z equals to pi t d square by 4. Clear? In the exam, whenever you have this table, you just want to take compare your bulk configuration with the geometry, and after that you select the formulas for uh, polar moment of inertia and the section modulus. So from this figure, we have now seen that the value of first we have compared our belt configuration with the configuration given in the table. And after that, we have to pick the formulas. So in this case, we have the formulas such as pi t d cube by 4 for polar moment of inertia and pi t d square over 4 for section modulus. Clear? Now we have to find these values. So just put these values here. So tau T1 is equals to P is 2000. E the distance from this point of application of load to the center of the rod. If you look at this diagram, this is 50 centimeter. From center of this rod to center of this rod is 50 centimeter. 50 centimeter means 500 mm, and D by 2 diameter of rod is 3 centimeter, which is 30 mm over 2, and J is T. By the way, again you know that T is 0.707 S. So we just write pi into 0.707 S into what is D? This is the diameter of the inner diameter of the weld, which is the outer diameter of rod, and that is 15. Sorry, that is 30 millimeter cube over 4. If I just solve this value, 2 into 2, 4 into 2000 into 500 into 15 divided by pi into 0.707 into 30 power 3, you get a value of 1000.5 divided by S Newton per millimeter square. Just check the calculations again. 2000 into 500 into 15 divided by pi into 0.707 into the 30 power 3. Okay, 4 into 2000, 500 multiplied by 15. I said 1000.5 divided by S. This is tau T1. Now sigma B1 is nothing but M over Z. Moment divided by section modulus, where moment is P into L divided by Z. What is the L distance? As a distance from this point to this point. So this is your bending arm, which is again 50 centimeter. Clear? The distance from this point to this point is called bending arm. So that is also 50 centimeter. The load is translated here is as 2000. So this is 2000 into 50 centimeter, sorry, 500 divided by z is pi t d square over 4 pi into 0.707 s into d is 30 square divided by 4. Again, you don't know, and I just want to mention here that the z is the relation of z is from the table, and that is pi t d square over 4. This is I have picked it from the table where t is equal to throat, and in all the cases in the well problems, this t is equals to 0.707 s. Okay, if you put the value, so and solve it, I just solve here to 4 into 2000 into 500 divided by pi into 0.707 into 30 square. You get 2001 divided by s Newton per millimeter square. So we get three values in case of load 1, tau d1, tau t1, and sigma b1. Now stress is due to load 2, which is P equals to 2500 Newton. Clear? So we have to find for tau d2, which is P over A, or you can say in this case just write P1 here, write P1 here, and P1 here just to in case to differentiate between two loads. P2 over A, P2 is 2500 because the weld is same, so area will remain the same, which is pi dt. So pi d and t is equals to 0.707 s. So 2500 divided by pi into 30 into 0.707 s. So 2500 divided by pi into 30 into 0.707. Answer will come out to be 37.5 divided by s Newton per millimeter square. Now for tau T2, it's T, or just write here T2, sorry here T1, sorry, this is for P1, T1. T2 into R divided by J. Because weld is same, so J will remain the same. Only difference between this is P2 into E into R divided by J. J is same because weld is same. If weld is different, then J of weld will be different. In both these lobes, these are applied on the same weld. So that's why the only difference is between P. So P and E. So distance, because of this, see this load is has an additional moment arm. From this figure you can see this is an additional moment arm of 20 centimeter. The total bending moment is 50 plus 20. So they see this load is applied on the extended arm. So in those cases, what we have is P2 is 2500 and E is 50 plus 20, 70 centimeter or 700 millimeter, and R is same, which is 15, and J is same, which is which is pi into 0.707 s into d cube. Sorry, d is 30 into 30 cube divided by 4. So tau T2 is equals to, this is 2500. So 2500 into 700 into 15 divided by pi into 0.707 into 30 power 3 multiplied by 4. So it's 1750.8 divided by S Newton per millimeter square. So we will find out another value which is tau T2. The last value is for sigma B. So sigma B2 is equals to M2 over Z. Sorry, there is a problem. Sorry. In case of the torsional shear stress, this is for the bending arm. The torsional shear arm is same, which is this. Sorry, I'm again repeating. For torsional shear stress, this will remain, the arm will remain the same. So instead of 70, we will write 500. Sorry. Reiterate again. Just reiterate again. I'm again repeating. This is for torsional shear. In case of bending moment, yes, we have additional arm, but not in the case of torsional shear stress. So 2500 into 500 into 15 into 4. This actually 4 come out in the numerator, divided by pi into 0.707 into 30 power 3. That is 1250.6 divided by S. This is the actual value. Sorry. For the bending stress, which is equals to P2 into L, 2 divided by Z. Because weld is same, so Z is same. But see, in case of this, we have additional arm which is 20. Now, in case of bending moment, we have this 50 plus 20 because it's a bending arm. See, load is loaded pressure. This is the bending arm. So the load is 2500. The L is 500 plus 200. That is for the case of bending. Divided by Z is pi into 0.707 S into D is 30 square divided by 4. So sigma B2 is 4 into 2500 into 700 divided by pi into 0.707 into 30 square. We get a value of 3501.7 divided by S Newton per millimeter square. Clear? Okay. Now what we have to do is now sum up, because all the stresses are in the same direction. We have to sum up the same nature of stresses. The first, all the shear stresses, and secondly, all the normal stresses. So we can say that tau R is equals to tau D1 plus tau T1 plus tau D2 plus tau T2. For sigma R, it is sigma B1 plus sigma B2. Tau T D1 is 30 over S. Tau T1 is 1250.6 over S. Tau D2 is 37.5 over S, and tau T2 is, sorry, 1250 is for tau T1 is 1000.5, sorry. Tau T1 is 1000.5 divided by S, and tau T2 is 1250.6 divided by S. Taking as common and just adding the numerator values, So 30 plus 1000.5 plus 37.5 plus 1250.6, you get 331. Okay, 30 plus, sorry, plus 1000.5 plus 37.5 plus 1250.6, you get an answer of 2318.6 divided by S Newton per millimeter square. For the bending stress, no, we have to add two normal stresses. The bending stress in case of one is 2001 divided by S. In case of two, it's 35, sorry, plus 3501.7 divided by S. So it's become 4502 divided point 7 divided by S Newton per millimeter square. Just to confirm, sorry, it's not 4, it's 5. 5502.7. So total shear stress in the circular weld is 2318.6 divided by S Newton per millimeter square, whereas total bending stress is 2502.7 divided by S Newton per millimeter square. Now, what we have to use a Mohr circle formula, and I think, sorry, we have to find it from the lecture slides. Yes, from the lecture slides, we know that now in the problem, what is given the problem? In the problem, the yield stress is known. So we can use either the normal stress formula or the shear stress formula. Clear? So we use the we preferably use the shear stress formula. Tau maximum. So just go back to the board. So tau maximum is equals to 1 by 2 under root sigma b square plus 4 tau square. In this case, it's sigma r and this is tau r. And sigma maximum is basically, sorry, tau maximum is tau allowable. And tau allowable can be found by sigma y over 2. This 2 is for maximum shear stress theory plus, sorry, into factor of safety, which is 1.5. This is 600. And because I'm using Newton per millimeter square, so again, remember, don't confuse it. 1 Newton per millimeter square is equals to 1 megapascal. So because I'm using all the units in millimeters, so I'm also using the stress in millimeter as well. 600 divided by 3. So it's 200 Newton per millimeter square. So if I put this value here, so 200 equals to 1 by 2 square root of what is sigma r, which is 5502.7 divided by S plus 3501 divided by S. Clear? Now we have to solve it for S. So S will come out to be, if I take S common, so this, sorry, this is square. So S will become S here. So if this is S square, this will become S here. They will remove S square. This come out to be S. If I take S on the right hand side, this will become 1 over 400. Sorry, 1 over 400 into 5502.7 square plus 3501.7 square. square root 3501.7 square. S will come out to be square root of 5502.7 square, Jama 3501.7 square, 5502.7 square, Jama 3501.7 square divided by 400. So value will come out to be 16.3 mm. This is the size of the weld, and it's a reasonable size. If you look at the, I don't know what is the answer uh, in my notes, but this answer is a reasonable answer. Normally, the weld size is ranging from 2 mm to 30-40 mm. If your value comes within this range, it's 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 an indication that you have solved the problem correctly. Otherwise, if your value say let's say 0.01 mm or zero point 0.1 mm, or it's 500 mm, 400, 100 mm, even 100 mm is sometimes fine for a very heavy loads, but generally this is not the case for most of the kinds of loads. So that's why this is our critical problem. If the same problem, I'm just repeating, I've been importing the problem again, and just to give you a case that in case of a problem in which you have the loads are, let's say, at an angle, clear? So let's say this is in this direction, this is in this direction. For example, this angle is let's say 45 degree, whatever the angle is. This is 30 degree. What you have to do, the only difference is if you look at the free body diagram. So this, let's say P1 can be resolved into two components. One is this and one is this. If this P1 is equals to 2000, sorry, and this angle is 45 degrees. So this component is P1 sine 45 degrees, and this component is P1, sorry, sorry. This component is P1 cos 45 degrees, and this component is P1 sine 45 degrees. So the vertical, which is P1 sine 45, actually have the same concept as we have applied here. It will generate three kind of stresses, which is tau D1, tau T1, and sigma B1. The only difference is now instead of putting P1, we just put, instead of P1, we put P1 sine 45 degrees. Or in this case, you can find it. So let's say P1 sine 45 is 0.707 into P1, which is 2000. You can put the direct value, which is let's say 1414.2 newtons. You can also do that. Now the horizontal component, which is like this, and if I just, let's say it's a horizontal component like this, it can generate two kind of additional stresses. If I translate this at this point, it can generate a direct shear. So if I just draw a free body diagram, three stresses are same. One is tau D1, tau T1, and sigma B1. These are the same as before. The only difference is instead of now putting P1, we have to just put the vertical component, that is P1 sine 45 degrees. Now because the horizontal component, we have an additional two stresses. One is direct shear in the direction of the horizontal component, and that is, we call it tau D, let's say we call it tau D1 prime. Just in case you have difference between D1 and D1 prime. Clear? And see, this cannot create a rotational effect. The horizontal component cannot create a rotational effect. The only effect it can create is the bending stress. So it can create bending in this direction, which tends to rotate in this direction. Clear? This beam tends to rotate in this direction. Clear? And that is probably anti-clockwise. So the bending direction will be the same as that of the direct shear. So this is sigma B1 prime. Similar in the case of uh, similar is the case for second load. This vertical component, so this P2 has two component. One is this and one is this. If this angle is 30 degrees, so this component is P2 cos 30 degrees, and this one is P2 sine 30 degrees. This P2 sine 30 degrees has the same effect as we have done the problem. That it has a tau T tau D2, it has a tau T2, it has a sigma B2. Same in the same direction because the vertical component. But its horizontal component is now in the opposite direction as that of first component. So it has a direct shear in this direction and bending stress in this direction. So we have direct shear in this direction, which we call it, let's call it tau D2 prime, and we have sigma B2 prime. So this is the case in which you have the load at an angle. Clear? So we have additional stresses due to the horizontal component. One stress is direct shear, and second stress is the bending stress. There is no other kind of torsional shear because horizontal component cannot rotate a body about its centroid. Okay. Now because we have now different directions of C, so what we have to do additionally, just in case you want to know and just elaborate here. So first you find resultants of these uh, all these stresses. Just adding all three shear stress, we have a resultant shear stress in this direction by another shear stress same as we have done before, which is the sum of all four stresses like this. Simple. And the bending stress is same, which is the sum of which is sigma r. Now, if you look at the problem, now we have additional stresses tau d1 here, clear, and we have sorry tau t2 prime here in sigma b2 prime. Similarly, we have tau d1 prime, we have sigma b2 prime. Now, what we have to do now is try to find the resultant torsional, resultant bending and the resultant uh, shear stress. So first of all, you have to just add these two opposite stresses here. Now because we don't know which one is the preferable, which one is higher than the other. If you know the magnitude, you can definitely you have to subtract it. So you can say, let's say its resultant will become this is resultant of the stresses that is on the same direction. Okay. Now let's say we take this direction. We're considering that sigma d1 prime minus sigma d2 prime. Clear? And for this case too, sigma b sorry 1 sigma b1 prime minus sigma b2 prime. I hope you understood. Now it's very important to understand that we don't know what is the actual direction. It could be here, it could be here. What we are considering is that sigma d1 is greater than sigma d2 or sigma b1 is greater than sigma b2. It could be opposite, but the formula is squares, so we do not have a concern of this minus sign. Now what we have to do is find the resultant of these two. Resultant of bending and the resultant of shear. How we can find that? This is simply because we have to find it by using a right angle triangle. So sigma r square prime square is equals to sigma, sorry, tau r square is equals to tau r square plus this tau d1 prime minus tau d2 prime whole square. Because this is known, you can find the resultant shear stress like this. Similarly, if you have the uh, similarly for the bending stress, same is the case. Just sigma r prime square is equals to sigma r square plus, now this is, you have to also add the difference, which is sigma b1 prime square, so not square, plus sigma b2 prime whole square. Here you can find tau and sigma r, and after finding these two values, we then have to find the, using this formula, we have to put those values here to find the size of the vent. This is a difference between two. The only difference now, instead of direct adding, you have to use the vector sum. And when the stresses are opposite, if the stresses are in the same direction, like if this load is also in this direction, so there's no problem. These two stresses will directly add up. Just add these two. But if they are acting in the opposite direction, and generally you have a difficulty of finding which one is greater, even if you know from the magnitude, you can easily draw that figure. So if sigma, the tau d1 is higher than tau d2, just write it. But because the formula contains square, there is no problem with the negative sign, because negative sign will dissolve in the square. So that's why we have to solve the problem in which the problems are like this. Now, if this same problem is the same problem come with a rectangular beam. So look at this. If I import a same problem, you can only able to solve these problem in exam if you practice those problems. The cases I am actually uh, taking it in this lecture. Just try to solve those cases. If instead of a circular beam, if this is a rectangular beam like this, clear? It's a circular cross section. This has a rectangular cross section. Clear? Now, and the difficult case is we have weld at two sides. So let's say the same case, I am doing it the same problem. I'm doing it for the just in case I'm solving it so that you know the idea. So the same problem has a beam. Just rubbing it again. I want to draw it again so you'll be more clear of. So instead of this, you have a, sorry, the lines are not straight. Sorry. So we have a, okay, we have a rectangular beam, clear? And the weld is only at these 2 points. It's a non-symmetric type of beam. Now we have seen this case in case of plates, but it can also come in beam, clear? And just for the sake of understanding, I just take it these at an angle, so I can take it as opposite angle, so that this could be, you can understand easily. So this angle is 25 degrees. This angle is 50 degrees. For example, just in case you want to understand. So loads are not at the but the magnitude is same, which is 2000 and 2500. But now the beam is rectangular, and the weld is the instead of the rectangle, instead of the a uniform or you can symmetric weld, it has an L-shaped weld. Now, what kind of stresses are there? So first, I tends to draw a diagram for the weld. So this is my configuration of the weld. Okay. Now for this case, I'm assuming some dimensions. So let's say this is a width of, for example, 4 centimeter and the height of uh, 3 centimeter. For just in case to understand, it could be anything, but just in case. So this dimension, I'm considering it as 40 mm or 4 centimeter, and this dimension I'm considering it as 30 mm or 3 centimeter. Clear? And this is the non-symmetric weld in both cases. I just want to know how many stresses are there in this beam. So first thing I have to find the centroid of this. So centroid is some now here somehow lies here, where this distance is considered as x, this considered its distance as y. Now first we have to see from a table. So if I import this table here, and from the table you can see that if we compare the welds here, so this is your L, sorry, this is your L, and this dimension is B. These are the unsymmetric welds. Clear? At both places. So we have to find x and y. X equals to L square over 2L plus B, and y is equals to B square over 2L plus B. Distance from the top and the sides. So, okay. Now just finding the values. X equals to, what is L? L is 40 square divided by 2 into 40 plus 30. If I solve this, 40 square divided by 80 plus 30, that is 14.5 mm. Distance from this distance is 14.5. Calculating the value of y, the b is 30 square divided by 2 into 40 plus 30. Sorry, I think I've done something wrong. Just hold on. Okay, yes. I've taken the formula wrong. This is 2 into, not multiplied by only 40 is multiplied by whole. So this is 2 into 40 plus 30. So it's 440 square divided by 140. Yes, the answer is different. Sorry. It's 11.4 millimeter. In case of Y, it's against the 30 square divided by 70, or you can just write 140 instead of. It's 6.4 millimeter. So distance, this is 6.4. Clear? Now we have located the centroid. Clear? Uh, Now we have how many kind of forces? Yes, it's a complicated problem. It takes a lot of time. And it's a long problem. This cannot become an exam because it's a lengthy problem. But just giving an idea that if you have a combination of all these forces, now the same stresses exist which we have for the this, let's say for this 200 Newton, we have two. This angle is 25 degrees. So this will become the cos component. So 2000 into cos 25 degrees. This is the 2000 into sine 25 degrees. This is P1. Clear? Just now finding the magnitude. So cos 45, so not 25 into 2000. This is 1812.6 Newton. This force, and this force is 2000 into sine 25, which is 845.2 Newton. Similarly, in case of the P2, we have this load, which is P2. It has the angle which is from horizontal, and that is, so from vertical, that is 50 degrees. So this component is the cos component. So P2 cos 50 degrees, and this component is the sine component, which is P2 sine 50 degrees. And P2 is 2500. 2500 into 2500 into cos 50 degrees, which is 1606.9 Newton, and P2 sine 60, which is P2 is 2500 into sine of 50, and that is 1915.1 Newton. Clear? So now we have four different kinds of loads. Clear? So if I just translate a load here, just importing this figure again, instead of this, just write the loads again. So loads are, now we have a load in this direction and in this direction. Okay? We have two loads, and we have also two loads, one in this direction, one in this direction. Clear? And the configuration is now L shape. Clear? So the horizontal due to P1 is, horizontal due to P1 is 845.2. Just write okay. Yes, this is 845.2. The vertical component is 1812.6. This horizontal component is 1915.1. And this vertical component is 1606.9. So we have four components, and even the configuration is an L shape. Clear? Now, because we have find the centroid now, so for each load, let's say load, and now we have found the stresses for each load. Just for law of free body diagram. Okay. Due to 1812.6, you can call it 1 P1V. Clear? P1V is equals to vertical force, one force in the vertical direction, downward. So what are the stresses? So this has three kind of stresses. One is bending, that acts downward, clear, on the centroid. This is sigma B1V, and then we have direct shear, which is again acting downward, which is tau D1B, and then we have a torsional shear stress because it's a uh, it's a non-symmetric weld, cell concentration on concentrated only at the free ends, and we know the distance. This is 40 centimeter, this is 30 centimeter, and we know the distances from previous x and y. So the torsional shear will be, because it's done to clockwise, torsion will be, this is called tau T1 V. Clear? So we have, sorry, this is the arm. Clear? These are three stresses due to P1V. Similar is the case for P1H. For this stress, which is 845.2 Newton, this force only has two effects. One is the bending stress, that is in this direction, which is sigma B1H, and the direct shear, which is again this direction, same direction, which is tau D1H. This horizontal component cannot produce any torsional shear. So that is the case. Now, in case of the P2V, which is 1606.9 Newton, we have again three kind of stresses. One is, and similar is the case here. The torsion shear would be in this direction too. Tau T1V. Clear? Okay. For the second load, we have again two kind of stresses. Three kind of stresses. Sorry. For the on the centroid, we have the tau D1 2V, because it also produces bending downward in downward direction because it's a vertical load. So we have sigma B2V, and we have uh, torsional shear, which is again in the same direction. This is tau T2V. This is tau T2V. Clear? And because the horizontal component is acting in this direction, so we have a direct shear in this direction, which is tau D2H, and we are bending in this direction, which is tau sigma B2H. Clear? So these are all the stresses that exist in the system. So what we have to do is try to sum up all the stresses. First of all, quantify all these stresses. It will take some time to quantify, but just we try to do that in this problem. So let's find first tau, sorry, not, sorry, tau D1V, which is P over A. Clear? We're going to P1V over A. Now P1V is 1812.6. Now area is the area of this L-shaped weld, which is 0.707 S into 30 plus 0.707 S into 40. Why? Because we have two welds, one is the length of 30, one is the length of 40. So 0.707 into 40 plus 0.707 into 30, 49.5. And if we divide it by 1812.6 divided by 49.5, you get 36.6. 36.6 divided by S Newton per millimeter square. Instead of just directly finding T2V here, because the areas are same, so that's why this T2V divided by A. The only difference is the area. Just if we directly find that, which is 49.5 S. So P2V is 1606.9 divided by 49.5 S. If you calculate this value, this will become 49.5 S. So 1606.9 divided by 49.5, you get 32.5 divided by S Newton per millimeter square. Now finding for tau D1H. which is P1H over A. Now P1H is 845.2 and the area same, which is 49.5 S. Clear? 8 845.2 divided by 49.5, which is 17.1 divided by S Newton per millimeter square. Similar the case for tau D2H, which is P2H divided by A, and P2H is, just writing, do not mention P2H. P2H is 1915.1 Newton. So 1915.2 divided by 49.5. Just to verify again the value of 49.5, the area, just in case we do not getting any fault in the answers. Yes. Okay. So 1915.2 divided by 49.5, you get 36.7 divided by S Newton per millimeter square. Clear? These are all. Now we find the bending stresses. P1. So what is? Now we are quantifying it. P1BV, which is M over Z. Now we have to now find Z. Or again, it's PB2B, which is M1B. This is M2B. We are bending in horizontal direction as well. So this is B1H is equals to M2H by Z, and B2H is equals to M2. This is M1H by Z, M2H by Z. Now Z is same for all because weld is same. So Z for the this beam, we have to take it from the table. So because this is this configuration, now Z is top and bottom. Now this is very important. Just see here. If your weld is upper leg is like this, it's called top weld. This. If this is like this, it's called as the bottom weld. Clear? So if this is called top configuration, this is called bottom configuration. So please remember, you have to, if the same L shape is in the bottom, so then we have to use the this formula. So this formula is, just magnify it so we can write it. So this formula is Z is equals to T into 4LB plus B square divided by 6. Okay. And in case we have to need the value of J, we just write formula of J also. J is equals to T into B plus L power 4 minus 6 B square L square divided by 12 into L plus B. Clear? In case, because we have to find the torsional shear stress, that's why I'm using it. Okay. Now, finding these values, M1B. M1B is P1B into L1 divided by Z. This is P2B into L2 divided by Z. This is P2H into L1 divided by Z. This is P2H into L2 divided by Z. Now what is P1B? What is L1? L1 is the distance from this point to where the load along the line. This is L1, which is 50. Clear? This is your P1, P1V. So P1V and uh, P1H. Sorry, it's B. Sigma. The sorry, L1, L2 are same for these two loads, horizontal and vertical. Clear? So this is actually you can replace it as 1 and this is for 2. Clear? So P1V is 1812.6 into 500 divided by, and now we have to find Z. Sorry, we have not, we have to find Z. Z is equals to 0.707 S into 4 into, what is L? L is 40 into 30 plus, what is B again? B is 30 square divided by 6. So ये क्या आंसर आएगा? 40 into 30 into 4 जमा 30 square divided by 6, 4LB plus B square over 6. I'll just see the formula again, so there will be any fault in that. So that is 4LB into B square divided by 6. Okay. So 4 into 30 into 40 plus 30 square divided by 6 into 0.707. This is 671.6 divided by S millimeter cube. So this is 671.6 divided by S. Clear? Similar is the case. P2V is P2V is uh, sorry P2V. Okay, for vertical load. Sorry, this is an additional arm which is 50 plus 20. I repeated here. So this is P2V is 1606.9, and because we extended arm of 20 mm more, so 671.6 divided by S. For P1H, this is P1, so the arm is 50. This is the same moment arm, which is 50 centimeter. So the P1H is 845.2, 845.2 into 500 divided by 671.6 divided by S, and sorry, this is written in the previous case, it's written correctly. And for PB2H, sigma B2H, it is P2H, which is 1915.1. And now because this is this load, so we have additional 20 mm arm, bending arm, which is 700 divided by 671.6 divided by S. I'm just removing these formulas here just to write the formulas, just write the answers. So just to write the answers of it. So sorry, this is not divided by S. I'm really sorry. This is not divided by S. This is actually multiplied by S. So 1812.6 into 500 divided by 671.6. So it's 1349.5 divided by S. I'm not writing units, but the units is Newton per millimeter square. Just the space is small, so that's why I'm not writing units. But you have to write units in the exam. It's very important. 1606.9 into 700 divided by 671.6. You get 16 74.9 divided by S. 845.2 into 500 divided by 671.6, you get 629.2 divided by S. And for the last case, 1915.1 into 700 divided by 671.6, you get 1996.1 divided by S. So this is for all the bending stresses. So first we are finding all stresses, all direct shear stresses, and now we have found all bending stresses. Third case, we have to find all torsional shear stresses. So tau T1 is equals to T1, because the torsional shear is only produced by vertical components, so there is no torsional shear due to horizontal components. So we have only two torsional shears. I'm again repeating that the horizontal component is not able to rotate it. It can only able to either direct shear, or it's able to, you can say, uh, bend it. But there will be no torsional shear. That's why only two torsional shear exist. So tau 1 R over J, and tau T2 is equals to, you can, R1, tau T equals to T2 R2 over J. Now because R2, for R2 we have to look back at the geometry again. So this is the geometry. So we have to first find this R and this R. This is R1, this is R2. I have to find theta also. Clear? So for this triangle, this value is, sorry, this value. So just if I separate this triangle from here, you can also do it in exam as well. This is your R1. Now this dimension is 40 minus 14.5. So 40 minus 14.5. That is 25.5. Clear? And this dimension is 30 minus, or in fact this is 6.4. So R1 is square root of 25.5 square plus 6.4 square by Pythagoras theorem. Clear? That is 26.3. So R1 is 26.3 mm. For this triangle, I've just separated this triangle. So this is your R2. This distance, as we know, is 14.5. This distance is 30 minus 6.4. That is 23.6. So according to Pythagoras theorem, we can find it by, that is 23.6 square into 14.5 square is 3, sorry, oh, sorry, is 27.7 mm. 27.7 mm. This is R2. And we have to find the angles, this angle and this angle. Clear? So the angles is, this angle is uh, tan inverse of 6.4 divided by 14.1 degree. 14 point, and this angle is, or this angle is tan inverse of 14.5 divided by 23.6, 31.6 degrees. So this is 31.6 degrees. Clear? So we now know R1 and R2. So now because the torsion shear is on the free end, so this R will be the same. Clear? R2 the distance of two possible points where the stress is applied, but R is the same. The distance from either R1 or either R2. So we have to find both stresses at both corners. One with the R1 and second with the R2. So you can call it as 1 and tau T1 prime and tau T2 prime. This is the slight difficulty in those problems because we have two free ends and stress concentration is on both free ends, and that's why, because R is different for both edges from the centroid, that's why we have to find four torsional shear. Before that, I'm actually saying in the lecture that you have to find two torsional shear. Yes, that is for the one point, but because R is different for both points, the distance from centroid to the both points are different. We have to find two torsional shear stresses for two different points. So this is T1 is P1, and because only vertical component can exert a torsional shear into the same 50, the angle is same, into 50, 500 into R1. R1 distance from, let's say, from the first point, which is this R1, and that is 26.3. 26.3. Now we have to find J as well. So J is equals to T into B plus L power 4 minus 6B square L square divided by 12 into L plus B. And now B is, again, just in case you get a fault in it, uh, B is 30. So 30 plus 40 power 4 minus 6 into 30 square into 40 square divided by 12 into 30 plus 40. So 70 power 4 minus 6 into 30 square into 40 square divided by 12 into 70 into 0.707, that is 12936.4 s millimeter 4. Just see the formula again, just calculating again so to get any fault in it. 70 power 4 minus 6 into 30 square into 40 square divided by 12 into 70 into 0.707. Yes. Okay. So this is P1. We, instead of writing P1, just write the value here. So P1B is 1812.6. So 1812.6 and divided by 12936.4 S. So 1812.6 into 500 into 26.3 divided by 12936.4. The value is 1842.5 divided by S Newton per millimeter square. Similar is the case for P2, that is for the second load, second vertical load, and that is P2V, and that is 1606.9 into the same torsional arm, which is, as you can see from the figure, and R is now the same, which we're using the same R, and that is 12936.4 S. Clear? So 1606.9 into 500 into 26.3 divided by 12936.4, value come out to be 1633.4 divided by S, Newton per millimeter square. Now, because for the second edge, which is this edge, the distance different, so that's why we have to find again the torsional shear for this edge. So T1 R2 divided by J, T2 R2 divided by J. So that is the same 1812.6 into now R. So the load into distance is same 500. Now the R2 is in this case is, we have find it, the R2 is 27.7. So it's 27.7 divided by 12936.4 S. That is 1812.6 into 500 into 27.7 divided by 12936.4. That is 1940.6 divided by S, Newton per millimeter square. And for the second stress concentration point for R2, it's 1606.9 into same into 27.7 divided by 1293.6.4, and that is the 1606.9 into 500 into 27.7 divided by 1293.6.4. You get 1720.4 divided by S, Newton per millimeter square. Now we quantified all the stresses. So we have actually four direct shear, four bending stresses, and we have four torsional shear. Now we have to now vector sum all these. So first of all the same stresses that are in the same direction, we have to add it together. Clear? So just in case, if I just uh, uh, okay, just draw a diagram here. So just a slightly bigger diagram so that we can add these two. This is for, you can also, I'll draw a big diagram in the exam. So we have to shift all the stresses to the concentration points. Clear? So let's see what happens with the first stresses. So these are the two direct shear and two bending stresses. You just directly add these two. Clear? So this is, we call it tau ds and tau sigma bs, which simply means that we have added both torsional shear and the, so these are the two stresses, sum of these two stresses. Similarly, we have two direct shear here. This is tau sorry, tau d2h, tau d2h. This is tau d1h. We have also bending stresses here, which is sigma b2h right side, sigma bh on the left side. Clear? These are the four stresses, direct stresses, and uh, we have torsional shears, two short torsional shears, and this is the distance from centroid. One torsional shear is in this direction, Second also in this direction. This is tau T1, this is tau T2, and we have also the another, this is tau T1 prime, this is tau T2 prime. Again, we have to sum all these stresses. So this tau ds is a sum of tau d tau d1v and tau d2v. ठीक है? So tau d1v and tau t2v is 36.6, 36.6 plus 32.5, 69.1. This is 69.1 divided by S. Clearly? Similarly, for sigma b, which is again both in downward directions, sigma b1b and sigma b2b. Sigma b1b is 1349.5 and sigma b2b is 1674.9, 3024.4. This is 3024.4. This has also sum these two because it's on the same direction. We call it sigma tau r prime. It's called sigma tau r. Clear? Because in the same direction you can add, so the stresses become smaller. So there is less number of stresses and you add these stresses. So sigma tau 1 and tau 2, which is 1842.5 plus 1633.4, 34, 34, 3475.9 divided by S. If your top prime 1940.6 plus 1720.4, 3661. This is 3661 divided by S. So now our stresses are reduces to, I'm just draw free body diagram. In the exam you can use multiple free body diagram, no problem. Okay. In the free body diagram you now have the tau tau tr, tau tr prime, and we have to translate these stresses at the free at this point. So this is tau ds, this is sigma bs, this is tau d2h, this is sigma b2h, this is tau d1h, this is sigma b1h, and similarly here. This is tau ds, this is sigma bs, this is tau d2h, this is sigma b2h, this is tau d1h, this is sigma b1h. Now see, there are 2 points in which you have to concentrate all the triangles, all the vectors. Now from now onwards you have to sum of these to find the sum of these triangles. Now as you can see in the diagram that this resultant is in the direction of the stress, the direct shear and the torsional shear, which certainly means that its component will be added in it. Whereas if you look at this tau r prime, its component is on the, which means its vertical component is subtracted, which you can assume from this, even in the exam, that the at this point the stress will be, overall stress will be smaller. Why? Because one of the component torsion shear will be subtracted, and that is generally the case when we have more complex geometry. You can find it from any of the point by just assuming that at this point, let's say at point I call it as point A or point B. This is point A. This is point B. I can argue that at point A because tau TR is in the direction of the other stresses, whereas tau TR prime is actually in the opposite direction, and that causes the stresses to be low because stresses will be subtracted. So I just take this point to find the size of the weld. So for that, I have to split this into two parts. So that's why it then become very easy to solve. So tau TR has two components, which is in one in this direction and one in this direction. So tau TR, and we have to find angle. So this angle we have find it. So this is 14.1 degrees. So you know we find this angle. So this angle is 14.1 degrees. So which means that this angle is also 14.1 degrees. Clear? So we have two components. This is tau TR because this angle is this is sine component, sine of 14.1 degrees, and there is another component which is tau TR cos of 14.1 degrees. So if I draw triangles again, so this is tau ds, this is sigma bs, this is the tau tr cos of 14.1 degrees, this is tau d2h, this is uh, sigma b2h, and we have tau tr sine of 14.1 degrees. Then we have another vector which is tau d1h and sigma b1h. Clear? So first of all, we have to shift triangles on one side, either on from left. So we just, if I take this, subtract this triangles here, and find the resultant of all the shear and all the bending stresses. So just just draw triangles again. So taking the sum of these two, so tau tr is 3 4 is 3475.9 into cos of 14.1 degrees, yes, plus this tau ds. See this tau ds, which is 69.1 plus 69.1. That is, so we have shear stress, which is, or you can just, you can see another like prime, just to call it prime. That is 3440.3. We have the bending stress, which is 3024.4. Now we have to sum these two shear stresses. Now we have to sum these two shear stresses as well as subtract it from it. Clear? So sigma tau d2h is, so it's actually become tau d2h plus tau tr sine 14.1 degree minus tau d1, because they are on the opposite direction. To subtract the, because we consider that right stresses are there are three stresses on the right side and two stresses on the left side. So there is a possibility that the stress the right side stresses are larger than the left side stresses. So what is tau d2h? Tau d2h, just go back to the previous slide. Tau d2h is 36.7. So 36.7, 36.7, yes, 36.7 plus. Now we have to find this. Tau tr is 3 4. These are all divided by 3 4 3475.9 into sine of 14.1 degrees. That 883.9. degrees minus what is tau d1. We have to subtract tau d1 because it's in the opposite direction. So tau d1 is 36.6 minus 36.6. See, the answer is 8. So we have call it as you get tau v prime tau h prime. That is equals to 846.9 divided by s. Clear? So we have a bending stress. For bending stress, we have to subtract it again. Clear? We can say whether B1H is larger, B2H is larger. Just look at the figure. B1H is two, 629. Oh, sorry, B2H is larger. Yes. So B2H minus B1H, which is BH resultant prime. Clear? So what we have is uh, subtraction of the highest value from the lowest value. The highest value is 1996.1 minus 629.2. So 1366.9. 1366.9 divided by. Now we have two shear stresses and two bending stresses. Clear? Just add, just find the resultant of these two. So resultant of shear is tau r and the bending is sigma b, and that will be simply for a right angle triangle. Just find the hypotenuse. So tau r is equals to 846.9 divided by s square plus 3440.3 divided by s square. Clear? So that will become 846.9 square jama 3440.3. Oh, 846.9 square jama 3440.3 square under root answer. You get this become 3543 point, okay, divided by s Newton per millimeter square. The resultant of the bending stress, which is called R is equals to the square of both, which is sigma bs, which is 1366.9, 1366.9 divided by s square plus 3024.4, 3024.4 divided by s square. So 1366.9 square plus 3024.4 square root answer, that is 3318.9 divided by s Newton per millimeter square. Clear? So now we have to use the Mohr circle formula, which is tau allowable is equals to 1 by 2 into sigma r square plus 4 tau r square. Clear? So tau allowable, as we have found in the previous numerical, that is 200, that is 1 over 2 into sigma b is sigma r is 3318.9 divided by s. Now 4 times, sorry, that is square. Okay, and the value is the resultant shear is 3543 divided by s. 3543 divided by S. Yes, square. So S is there, just find S value of S. So S from this is 3318.9 square plus 4 into 3543 square under root answer divided by 400. The answer is 19.6 mm. This is the size of the weld. So see, this problem is complicated because of two reasons. First, you have the asymmetric weld. That is the most difficult case. If you have a symmetric weld, definitely you have on both these edges the stress will be the same. But in case of non-symmetric welds in both planes, like L-shaped weld, the problem becomes difficult, and that's why you need to find the stresses at both these points. And secondly, we have two loads, and that's why every load has two components. So that's why basically there are four loads, and for every load you have to find all these stresses. That's why this numerical has been expanded. In the exam, definitely this problem is very lengthy, and you cannot solve it in the exam. So the exam gives a shorter version of this problem, but it could be any of the case. It could be there are two loads. One could be the horizontal, one could be vertical. There could be an angle at certain angle as we have seen it. So the important thing is try to understand those problems, try to understand geometry of the problem, understand how to perform a vector sum. If the stresses are in the same direction, just directly sum together. If they are at a certain angle or the 90 degrees, just take the resultant, which is by using a Pythagoras theorem. And last but not the least, if the same problem come with a plate, this is for the beam. Also I've given you a very difficult case in which the weld is unsymmetric and it is a beam that is in which the weld is unsymmetric. So an unsymmetric weld, we have torsional shear, we have bending shear, we have bending stress, we have direct shear. In case of uh, problem, which the plate problem which we have done in the class, so if the same problem comes with the uh, let's say with the non-symmetric weld like this. Yeah. The only difference between in plates, we do not there is no bending stress. And if it is at some certain angle, for example, so at a certain angle the vertical load can produce direct shear and torsional shear. And the horizontal can produce only the direct shear. So this is problem we have solved in the class. So in case of the angular load, we have a horizontal component and a vertical component. Vertical component produces the same stresses as we have done in the class. So on the free edge, so just draw here. On the free edge, we have a direct shear, which is this. We have a torsional shear, which is this, which is perpendicular, sorry, which is perpendicular to the centroid. Clear? Which is perpendicular to the centroid like this. And because the horizontal component, we have additional direct shear, which is so we call it PDB or called DH. So what we have to do is only perform a vector sum, which means that we have to divide this. We have a three shear stresses. Clear? We have to convert it into you can say into horizontal component and vertical components. Uh, yes. So we have to use, so this has two, let's say there is a certain angle called theta. So we have two, this is and this, we have two components. So this resultant, so this is tau t sine of theta, this is tau t cos of theta. And now the total horizontal stress will be tau t sine theta minus tau di. This is the horizontal component. Clear? And the vertical component is tau t cos theta plus tau d2. See, both are in the same direction, so we add together. But because these two are in the opposite direction, we just subtract together. And the resultant will be two stresses. One will be tau t sine theta minus tau dh, and lower is tau t cos theta minus plus tau d 2. Clear? So the angle between these two is 90 degrees. So cos 90 is 0. Uh, Sorry. Yes, cos 90 is 0. So when you apply this formula here, this whole thing vanishes. So you are left with only tau is equals to tau 1 square plus tau 2 square. So from that, let's say tau 1 is some like tau 1 is in this case you write as tau h square plus tau v square. The sum of the horizontal component of shear stresses and sum of the vertical components of shear stresses. Clear? So let's say this is, for example, this is 1000 divided by S, this is 800 divided by S. This is the tau allowable, like this is 200. So just find the S from here. Clear? This is the idea of if there's a prop angle, if there's a force at an angle. So just you have stresses, but in case where there is a beam in which the weld are non-symmetric, the problem becomes difficult, and that's why you have to consider all these stresses which are based on all different kinds of loads. And it's very important for you to practice these problems. Please practice it. Take different cases, take different angle of forces, and see what will come up with the size. The size again should vary from 2 mm to 30, 40 mm. It could not be 0.1 mm, it could not be 100 or 200 mm. I hope this lecture is beneficial to you. As I promised, I have actually recorded this lecture and provided to you. If you have any queries, you can come in the my office and can inquire about it. Thank you very much for your time and patience. Allah Hafiz.